Water, like any liquid, has certain properties. Some of these properties include boiling temperature, freezing temperature, conductivity, and so forth. What we're looking at in this recording today is how dissolving a solute in water or other solvents changes some of those properties. For example, we know that in order to protect the water in the cooling system of your car from freezing, you add a solute called antifreeze. There are other examples of this. Road crews put salt on roads to prevent ice from forming. These are properties of the liquid that are affected by dissolving a solute in them. We're looking at what are called colligative properties of solutions, and these are properties that depend not on the identity of the material being dissolved, or the solute, but rather on the number of solute particles that are present in the solution. We're going to focus specifically on three properties: vapor pressure, boiling temperature, and freezing temperature. As we have learned before, evaporation occurs when high-energy particles of a liquid reach the surface of a liquid and escape the bonds that hold them in the liquid phase. As these particles begin to fill up the surroundings, if the liquid is within a closed container, then as particles are escaping and filling up this container, particles also begin to occasionally randomly hit the surface of the liquid and recondense to form a liquid. When the evaporation rate and the condensation rate are equal, then we've reached the state of equilibrium. The pressure exerted by a gas in equilibrium with its liquid phase is called the equilibrium vapor pressure. Within a pure liquid, this is a property of that material. Now, when a material, a solute, is dissolved within that liquid, this reduces the number of particles of the liquid that are at the surface. Consequently, this then slows down the rate of evaporation, and equilibrium will be reached with fewer particles in the vapor phase. The rate of evaporation and the rate of condensation are slower with the presence of the dissolved solute than they were in the case of the pure liquid, because there are fewer high-energy particles of the liquid reaching the surface. So as a result, a solute dissolved in a solvent has the effect of reducing or lowering its equilibrium vapor pressure. Now let's take a look at the second property, the increase in boiling temperature. So the equilibrium vapor pressure is very closely related to the boiling temperature. If you will recall, boiling occurs when vapor pressure is equal to atmospheric pressure. So here on this graph, we have two lines, one representing the vapor pressure of a pure solvent, a pure liquid such as water. You can see that we have temperature here on the x-axis and vapor pressure on the y-axis, and as the temperature increases, so does the vapor pressure. If atmospheric pressure is represented by this line here, boiling then occurs when the vapor pressure is equal to atmospheric pressure. This second line represents the vapor pressure of a solution. Remember that at any given temperature, the vapor pressure of the solution is less than the vapor pressure of the pure solvent, due to the fact that there are fewer particles of the solvent at the surface. And this is true at whatever temperature we're looking. So for example, at this temperature here, this line represents the vapor pressure of the pure solvent at that point, and here at a lower vapor pressure is the vapor pressure of the solution. So if this is the pressure that's required, this is atmospheric pressure that's required for that particular liquid to boil, the pure solvent would boil at this temperature represented here by TO, the original temperature, boiling temperature. But it wouldn't be until this temperature, represented by T1, that the vapor pressure of the solution is great enough to equal the atmospheric pressure. The difference between these temperatures, the original boiling temperature and the temperature at which the solution boils, is called the delta T sub B, or change in boiling temperature, boiling point elevation. So to calculate the boiling point elevation, we use the following equation. The change in temperature of the boiling temp, delta T sub B, equals the molality of the solution, M, times the boiling point elevation constant, which is dependent on what solvent we're talking about. For water, this constant is a value of 0.512 degrees C per molality. So it's a fairly easy equation to use. Let's look at an example of this. So let's take the problem, calculate the boiling point elevation of a solution made by dissolving 150 grams of glucose in 250 grams of water. Glucose, if you'll recall, has the formula C6H12O6. So what we're going to do here is first calculate the molality. And the molality, of course, equals the moles of solute divided by the kilograms of solvent. So in our problem, we know we have 150 grams of the solute glucose. So we're going to have to calculate the moles of that first. We have 250 grams of water, so we'll put down here that we have 0.250 kg of water, because molality is moles of solute over kilograms of solvent. So we first have to find the moles of glucose to plug into the equation. So we have a mass here of 150 grams of glucose times our conversion factor of 1 mole of glucose over its molar mass. The molar mass of C6H12O6 is 180.18 grams. So in working this out, we end up with a molality here of, or with a number of moles here rather, of 0.83 moles. So now we'll come back to our equation and we'll put in the 0.83 moles of the glucose divided by the 0.250 kilograms of the water, and we end up with a molality of 3.32 there. So now we can go back to our equation and we'll plug in to find for the change in the boiling temperature 3.32 molality, 32 molality multiplied times the boiling point elevation constant for water of 0.512 degrees C per molality. So our molalities cancel, and we end up with a boiling point change in this case of 1.69 degrees C. And so our new boiling temperature of the water would be 101.69 degrees. So now let's look at a slightly different problem. Here we're going to calculate the boiling point elevation, as we did in the previous problem, of a 3.32 molality solution, but this time our solute is sodium chloride instead of glucose like it was in the previous problem. To understand why this problem is a little bit different, we need to look at the mechanism by which sodium chloride and glucose dissolve. So when we shake some salt into a solution, you'll see that it breaks down into its individual ions. The NaCl breaks down into Na positive ions and Cl negative ions. Now if we kind of compare that to what happens when we dissolve a covalent material such as sucrose or glucose, as in the previous problem, in water, we'll see that although each crystal breaks down into individual molecules, the molecule itself doesn't break down into individual atoms. So it's not quite broken down to the same extent as the ionic material was. Now let's look at how this actually affects our problem. So now when C6H12O6 glucose dissolves in water, the water is the agent which breaks down the aqueous solution, the solid into an aqueous solution. But the crystal remains intact, the molecule remains intact. It's still C6H12O6 before and after it dissolves. On the other hand, when H2O causes the breakdown of sodium chloride, each single unit of sodium chloride breaks down into a separate dissolved ion of Na positive and Cl negative. This happens to ionic materials, and this is called dissociation. And literally that means that the water causes the individual ions to dissociate or break down completely when they dissolve. So as a result of this, this changes our problem a little bit. Now, what happens is the molality of the NaCl is the same, 3.32, but when it breaks down, it produces a molality of 3.32 of Na positive ions and the same molality, 3.32 m of Cl negative ions. As a result, there are twice as many particles in the solution as then there were when we dissolved the glucose. So now, when we look at the problem, our change in temperature at the boiling point is going to equal the molality, 3.32, times the number of ions that it breaks down into, 2, times the boiling point constant for water, which if you recall is 0.512 degrees C per molality. So now when we multiply these together, we'll see that we have a change in boiling point of 3.40 degrees C, or twice that of the boiling point elevation caused by the glucose. And so our new boiling point of the water with this salt dissolved in it would be 103.40 degrees C. So an ionic material has a greater effect on the boiling point when it's dissolved because it splits down into more particles in the solution. Now let's take a look at our third and final property of solutions. So here we're going to look at how adding a solute affects the freezing temperature of a solvent such as water. So here we have an animation of water molecules in the liquid phase at a temperature just where freezing is about to begin. So let's lower this temperature down just a little bit and watch the freezing process take place. So you can see the effect of cooling down the temperature on the motion of the molecules is to slow the water molecules down enough that when they make contact with other water molecules, now they no longer bounce off and continue to move around, but they begin to stick together and form the hydrogen bonds that hold them together in their crystal lattice as ice. So this is for pure water. Now let's warm that temperature back up again a little bit, and now let's add a solute to the mixture. This is represented by the white particles there. So now you can see what happens is those solute particles move in between the spaces of the water molecules and prevent them from forming hydrogen bonds. Occasionally you'll see a bond begin to form, the crystals start to form, and then that formation be disrupted by the presence of the solute. So now in order for the ice to form, the particles of the water have to be slowed down to even a greater extent than they normally would in order to freeze. And you can see as I drop the temperature quite a ways down, now the ice crystals begin to form. So just like there was an equation to calculate the elevation of the boiling point, there's an equation to calculate the depression of the freezing point. You can see it written here. We have the change in the temperature of the freezing point, delta T, equals the negative of the concentration and molality of the solution times the freezing point constant instead of the boiling point constant. You'll notice for water that the freezing point constant is a little bit higher than the boiling point constant was. It's 1.86 degrees per molality. So let's look at a sample problem here, just like we did with the boiling point. So our problem is to calculate the freezing point depression of a 3.32 molality solution of glucose in 250 kilograms of water. We've shortened this by already having the molality calculated for you. So our problem then would become delta T equals negative molality times the freezing point constant, 1.86 degrees C per molality. Molality cancels. And when we multiply this, we get a freezing point change of negative 6.18 degrees C. Since water normally freezes at 0 degrees C, now the new temperature at which it would freeze would be negative 6.18 degrees C.